Hi everybody, today we are going to be writing down and deriving the equation for a flow system, or the energy formula for a flow system. So one way to think of what this flow system is would be a pipe. And then this would be the in, and this would be the out. And we want to find the change in this pipe with all the different parameters. And so you can think of this as the differential times the mass. As the differential is the very small change in everything we're going to be doing, it refers to mass. And then there's going to be internal energy plus kinetic energy, so that would be v squared over 2, plus potential energy, which we are going to call Gz. And all this is saying is that for the entire system, as this equation right now is for the system, everything would be internal energy, velocity, or kinetic energy, and potential energy. And all of these have the same unit, which would be kilograms per joule, I believe. And so we can actually express this into in and out. So let's do that. Again, everything has mass, and so we're going to take that out front. So we're going to start our in right here. It's going to be m times, let's see, u plus v squared over 2 plus gz. I have a really bad habit of writing things way too close. And then it's going to be multiplied by the differential of n, as that can change. So we're going to use that as a separate formula right now. dn minus the mass of u plus v squared over 2 plus gz. And this is d out. And so you can think of this d out and this dn just differentiating these different variables. Because if I didn't have this here and I just said it, I would most likely have to put, oh, this is u1, this is uv2, and just etc. And then there's a few other things that will go into this equation, which will be plus, I'm going to say dq, or either q or dq. Let me think real quick. We're going to say q, as it's going to be any, dq, as it's going to be any heat added, plus dw, which is going to be any work done onto the system. And what do we know about dw, as we spoke about in the last class? So dw, we know, equals p dv. But before I get ahead of myself, let's head back a second, as I want to talk about density and talk about our enthalpy equation I have written up in the corner. But I will write it right around here. So we know enthalpy equals internal energy plus pressure volume. And if you think about volume, you can think about as what we're talking about will be to a specific volume, or dmn. We can think about this as a specific volume. So that as u is going to be either per kilogram or per mole basis, we can think about it as a per kilogram. And what we know about density, let me write this down real quick. So we know that volume would be and what we know about density is mass per volume. And what we have here is volume, not mass per volume. Yeah, mass per volume. What we have is the volume per mass. And so what we would have to do is put the reciprocal, or kilogram over meters cubed, which is mass per volume, which actually lines up perfectly with our density equation. And so we can think of this as, or we can think of dw equals pdv as dwn, because it could be doing work either before or after, as what we're talking about is technically referred to as injection work, or injection in and injection out. So we would have dw equals p n over density n, right? Because it would be the reciprocal, because it's multiplied by the change in volume. it would then be divided by our change or our density. And so that would then be rho n. And if what we have is for in, we know that there's also going to have to be something for out. So dW is going to actually equal Pn minus P out over density out. As there could be, this could be a reactor in which what we're putting in could change density as it reacts, like a polymer. And so we realize that we can write this instead of in and out as D. Or if you look up here, we could actually input our P in and our P out into this primary equation. And so I'm going to rewrite this, but I'm going to erase what we've written here. Okay, and I'll try to remember to put this back in, as we're going to try and add it right after the U. So actually, let me erase this, and maybe I can kind of fit it in right there. So we would have M U plus P in over rho. Actually, we don't need to put in anymore, as the derivative or the differential of in specifies that for us. So we would just be P over rho, or the density, yeah, I think that's rho, plus G squared over 2, plus GZ, to the dN. Then we would subtract, as we've done this before, it would be M of U plus P over rho plus V squared over 2 plus GZ to the D out. And then what we did is we calculated, or we put in our work that is done onto the system, or like a uniformal work. However, or our flow work. But what we also have to include is our non-flow work, which you can think of as a stirrer or a mixer. Just anything that does work and is not really a part of the system. So D, W, and F. And let me erase something real quick. And again, I would like to direct your attention up to, well, before, I want to again specify that everything we have here is this equals, as this is for the system, and everything here is specified in either the in or the out, okay? And I want you to stare your attention up to here, to our enthalpy equation. As what we talked about earlier when we were transforming our specific volume into density, is that H equals U plus PV. And if we were to change the density in this equation, what we did like over here, we would have H equals U plus P over V, or not V, rho. And if you look at our equation, we actually have that in our equation. And so we actually want to combine these like terms into H, or enthalpy. So we would then get M of H then plus enthalpy plus kinetic energy plus potential energy. And again, I want to specify this as dN. Then we are going to subtract, like we done before, then mass multiplied by H plus V squared over 2 plus GZ. Right? Okay, it's making sure I'm still recording. Then again, multiplied by D out. And then what we're also going to add is this, as we've already spoke about this before. So we're going to also add DQ and our non-flow work. And from here, what we have, try and not circle everything I don't want to, is our equation for our energy formula for for a flow diagram, not flow diagram, for our system of a flowing system. That's what I wanted to say. So in B2, I took the liberty of, I'm getting ahead of myself. In B2, we are going to be finding Bernoulli's equation, which will actually fall out of this equation for the flow energy of the system. And so what I took the liberty of doing is rewriting the equation we derived previously. However, I didn't combine our U, or our internal energy, with our P over our density to get our H, or enthalpy. As what we're going to do is, for Bernoulli's, for Bernoulli's, it means it has to be at steady state. For being at steady state, that means that the differential of the mass of our system is 0. It means there's going to be this minus this plus this equals 0. And so for this to equal 0, that means we're going to have a lot of things, if not cancel, just change sides. And so I'm going to write it down in a little bit of a list order. So we're going to have 0 equals U2 minus U1, and then we're going to have V2 squared minus V1 squared, and then we're going to have, let's see, GZ, so it's going to be over 2, important. And then we're going to have, we're going to be G with a Z1, Z2 minus Z1. Actually, I'm just going to keep that together. It's just going to be GZ2 versus GZ1, or minus GZ1. GZ2 minus GZ1, and then we're going to have, let's see what else, P2 over rho 2 minus P1 over rho 1. And there's something I wanted to bring up really quick before I got back into this, as something I wasn't sure if I was very clear of was that in our equation we derived is that it's dm in for the differential of mass flowing in, then the differential of mass flowing out. I believe I had just written dm in, or just dn instead of adding the m, and that's really important for trying to understand this whole system. And so after we have that, we can start taking things to the other side, because we're going to have a few negatives and such. And so we would have, we're actually going to keep our internal energy onto the right side of this equation. So we would have, let's see, it would be P1 minus P2 over rho. And the reason I'm writing it like this is because this is an incompressible liquid, which means P1 is going to equal P2, as this is a part of what makes it a steady state. And so that means we can just write it like this. And then we're going to do plus V1 squared over minus V2 squared all over 2. And then we're going to add GZ2 minus GZ1, in which I still believe I can just, not 2, it will be 1. I still think I'm going to take back what I just said earlier. I'm going to take G out and then just put Z1 minus Z2. And that would end up equaling U2 minus U1 plus DQ plus DW and F. And something I'm not sure if you realized is that we divided by dm, or to get everything at one side, we had dm. And so what we're going to do is we're going to divide this by dm, divide this by dm. And I'm not sure if you realize this, but Bernoulli's equation is the density, or the pressures over the density, plus the kinetic energy, plus the potential energy, and it equals what you want, or the internal energy plus the heat added divided by the mass plus the non-flow work over the mass. And so what you have here is actually Bernoulli's equation. It just kind of falls out right in your hands. However, we are actually able to do something else with this equation. And I'm going to rewrite it over here real quick. So if we were to combine our U and our rho, or P over rho, that would be H. And something that happens in this is that if it's a steady state, it means everything's moving through the same it's going great, everything is equal, it's all going to equal 0. But the h's don't. So what we would get is we would get h2 minus h1, and we would multiply that by dm. Okay? And what we know about h is that h equals u plus pv. And this would equal 0. Sorry, I'm getting ahead of myself again. And so we can actually bring one of these to the other side. And so what I'll do over here is I'm going to bring one to the other side while at the same time converting it into this equation, except instead of v, we're going to have density. So we're going to bring this back into the fold. And so we would have not h1, I just said I wouldn't do that. I wouldn't do that. So we would have p1 over rho plus u1 equals, it would be p2, making sure you can see this, over rho 2 and over rho 1. Actually, again, we're going to state that rho, because this is a non-compressible liquid, will be fine. And so we'll have that. And then we're also going to add u2. And we're going to take these all to one side and or change up the variables, change them up, but bring all the same similar variables to the like side. So we would have p2 minus p1 over rho equals, we would have p21, so then it'd be u1 minus u2. And what we know about u1 minus u2 is that u equals cv dt. So over here we would have, remember that u equals cv dt, or the change in temperature. And so what we could have over here is this is the change in internal energy, and this is a constant. So we could bring the constant outside, and then this would turn into T1 minus T2. So we would have P2 minus P1 all over rho, which, let's say we're using our water in our pipe-like system that I wrote down earlier. That would just be maybe, I believe it's 1,000 kilograms per meter cubed, if that sounds right. And it would then equal CV times T1 minus T2. And that would end up, that's another way of, this wasn't exactly the Bernoulli's equation, but it's another thing that's very helpful in the certain scenarios, depending on what that might be. And so what we did is we calculated Bernoulli's, and we also calculated, I'm not sure the exact name for this equation, but I do know this will be useful in future problems. And just real quick, just to touch things up, I wanted to make sure that P2, or H2, can also be counted as Pn. So this would actually end up being Pn minus P out equals T out minus T2 or Tn. And this is mostly shown in the opposite form. So you could take the reciprocal and everything, and this would end up being P out minus P in over rho equals the CV of T, this is in, yeah, so T in minus T out. And this is just the way it's most commonly shown, and I wanted to make sure that didn't confuse anyone. So now we're going to be using the first equation we derived to calculate the increase of temperature of water if it were to go through a 9e to the 5th pressure drop, I think is the best way to describe it. So first, we have a few parameters. We're going to have PE is constant, so PE equals the same, and KE equals the same. And so what that leaves us is, if we remember correctly, it would be M, or let's do D, M would be PE plus KE. Or actually, I don't like writing like that. Let me actually write the terms. Sorry. So it would be H, when we had the pressure and the density, it would be H plus V squared over 2 plus GZ. And if we had V squared, and this is for the system, remember, so this is the whole thing. So if we had this to be constant and this to be constant, what we would have was we would have H in minus H out, which if you remember from last time, you slowly meander through it, and that would equal 0. You would get UN plus P, right? P, so it'd be P rho. P in over rho equals U out. P out over rho, which you can see. And because we're using water this term, that means the densities are going to equal each other. So I'm going to go over here. P1 equals P2. And I took the liberties again, so I didn't actually have to remember them on the fly. Remember the density of water per kilogram and the CV constant for joules per kilogram of water. And so from here, from us having UN and then PN and rho, we would separate terms. So we would get P in minus P out over rho, and that would equal that would equal U out minus U in. So we would have U out minus U in, okay? And what we know about U is U equals CV dt, in which we're going to calculate the dt. So I'm going to write over here again. So we would have P in minus P out, otherwise known as the change in pressure, over the rho, which would then equal CV of, that wouldn't be U anymore, that would be T out minus T minus T in. And this is the equation we would get. And so let's do with this real quick. So this would be 1e to the 6th minus 1e to the 5th, which would equal 9e to the 5th. So we would have 9e to the 5th all over, let's say 1e to the 3rd, which would then equal CV, we're 190. And then that would be T out, as that's what we're calculating, as we're trying to find the amount of heat that is gained when we lose this amount of pressure with the same velocity and potential energy. And so minus 298, as we were given that the temperature going in is 298 Kelvin. So what we would do is we would know this would cancel with that. So we would get 9e to the 2 all over 4, 190, and then you would add 298, and that would equal your T out. And if my memory reminds me correctly, I believe this is around 0.2 Kelvin. So it's not a lot, but this is not a giant pressure drop. So it can really be interesting about how this, what we calculate over here, this equation, can affect flow systems and how that increases the temperature. Now we're going to be using Bernoulli's equation, which we calculated in the second clip, to calculate the velocity of the air in a 10,000 Pascal pressure drop. I know it's most likely hard to see inside this box with a thin chalk, so I'll explain it to you. Inside of the box, we have the pressure is 10e to the 3, also known as 10,000 pascals, and on the outside it's 0 pascals. And so what we want to do is write our equation in terms to help us solve this. And so let's get to it. We know potential energy is going to, so we are going to be left with P1 minus P2 over rho plus V1 squared minus V2 squared all over 2. And if we go to say this is V1, that means right here is going to be V2. So I would think that would just leave us with a V2. But, anyway, I digress, and that equals 0. And if you see here, what we're given is, so it's the velocities squared, okay, along with the density, the pressures, which we know, and volumes. Actually, I believe we were given the volumes, but again, I will get through as far as I can without them. And then density. And we're using air, so to calculate the density of air, density equals mass over volume. We calculate mass. We know we want the amount of moles times the molar percent amount of each different gas. I believe there's argon and nitrogen. And so this is percent sign. But to calculate N over V, we use the illustrious pervert, the ideal gas law. So to have N over V, that means you would have P V over RT, and then take V over. So we would then be left with P times the molar mass over RT. And the molar mass of air, I believe, is around 29. And when you plug in pressure, as we would do, we would plug in pressure, and then we would plug in the R and the temperature. You end up getting 1 point, as we would do this at atmospheric, so this would be 1, this would be 29, this would be 8.3, and then this would be 273. You would get 1.2, as this would be in Pascal, so we 1/8 of the fifth, sorry. This would be 1.2 kilograms per meter cubed. All right, and from there, we would have our density, and we would actually have to go and plug it in. So, as what we would know is let's do it over here. We would have, again, I think V1 on the inside would be 0, and V2, the negative sign, is just referring to it leaving our system. And so this would be a 0 in the inflow, which is a big size. I think we're going to assume it's 1. And so that would end up being P1 minus P2. So that would be 10,000 over the density of 1.2. And from there, we would then multiply that by 2 while taking the square root. And I believe that equals 129 meters per second. So from just a simple 10,000 Pascal drop, the air would actually leave the system at 129 meters per second, which is a gigantic number. Just that's how, in class we were explained that this is how hurricanes are formed, just by this simple small pressure drop, which is about 1/10 of an atmosphere. That's just a huge number. And there we calculated, using Bernoulli's equation and finding the density of air, we calculated the velocity of the air leaving our system.